Welcome back to Muddy Math, where we take middle school math concepts that are a little muddy and clear them up. Today we're talking about how can linear expressions model real life. This was a question a lot of my students had last week with the Barnstable Public Schools 7th grade activity, the third example on adding and subtracting linear expressions in the Big Ideas math activity. So I want to dive in a little bit between the vocab and the concepts of why we might ever want to express ourselves with algebraic expressions, specifically linear algebraic expressions, in real life, and what this means for solving an example from a textbook using this skill. So I like to think about math as an interconnected web of ideas in my brain, and you can see here, like, these are all the ideas I came up with related to this concept. So I'm going to zoom in here. I'm probably shouting. Okay, and let's take a look at some of these vocab words. So, okay, operations with linear expressions. First, we need to understand what is a linear expression. You all might be familiar with operations. Operations are addition, subtraction, division, multiplication, square root, powers. There's more, but for now, I think in middle school, this should be good for you. In terms of, I'm squatting here, so this is a nice hamstring or quad workout. Okay. Now, terms. Terms are any combination of numbers and variables connected by multiplication and division. So in this example, negative 2x is a term because negative 2 is the coefficient and it's connected with x by multiplication. Even though we don't write it, there's multiplication between the coefficient and the variable. Putting a bunch of multiplication dots between a coefficient and a variable will crowd our notes. So whenever in math we can omit or leave out some sort of mark or notation to make our notes less crowded, we're going to do that. And this is the case. So you don't put a multiplication dot between a coefficient and its variable. It's assumed that the more you practice writing math, you just drop that multiplication dot. Hey, if you need to draw that multiplication dot in, until you're more comfortable with remembering that there's multiplication between a coefficient and a variable. Coefficient, right? Coefficient. And then variable here is x, x, t, x, x, x. You commonly use x with variables because it is related to the x-axis, the horizontal axis on the coordinate plane, which is where we often graph these types of relationships. So we just talked about coefficients. Now let's talk about constants really quick. Okay, constants are the numbers with no variable. Another time mathematicians omit or leave out some notation. Really, we could say this is t to the 0 power, and as you get more comfortable with powers and exponents, you'll see that anything to the 0 power has a value of 1. So t to the 0 power actually has a value of 1, and remember that invisible multiplication at 6 times 1 is just 1. So again, we mathematicians like to omit things that crowd our notations. So we have coefficients, we have constants, we have terms. Terms are separated by addition in an expression. So anytime there's addition, you know that that addition symbol is separating two terms. And in this case, these are non-examples, okay, but those are still terms, even though they're not linear expressions. These are algebraic expressions. Negative 2x squared plus 3x is a quadratic expression. And you'll learn about that in the future. Or if you're curious now, you can check it out now. But this is also not a linear expression because there's an inverse symbol here, meaning that the x is in the denominator, and when the x is in the denominator, it doesn't form a straight line. My dogs are about to bark. Hold on. Quiet. No barking. Good girl. No barking. Okay, please be quiet. Stay quiet. Please be quiet. No, Canella. Here, let me. Here. Hi, Rebecca. I see you. I'm going to try to get Canella to be quiet. Come here. Shh. All right. We're going to stay right here. Okay, shh. So Kanella's gonna help me. Oh, there goes Snoop. Didn't plan for this. Quiet, Snoop. Snoopy, quiet. Snoop, quiet, please. Okay. So, dogs don't like delivery people, and I hope that you guys are all enjoying the deliveries. This is Canella. Canella was saved from Costa Rica. We're taking a commercial break here. Canella is called a zaguate. We think she's a combination of maybe a boxer, a German shepherd. What else might she be? Chow or Shar-Pei. She has a black tongue. You see it a little bit there? Shh. And there's very few breeds of dogs that have black tongues. She only has a couple spots on her tongue, but there you go. Are we better now? The delivery, guys? She's kind of heavy, so this is quite the workout. Quiet. Good, Snoopy. Good, quiet. Snoop's in the other room. Okay, here we go. Quiet. Good girl. Sit. Good girl, Canella. All right. I hope you enjoyed the commercial break. Now we're back. Okay, so yes, Rebecca, it is a lot of notes, but remember, there's so many connected ideas in math, and yeah, a lot of people have dogs that are similar to Canella because she's a mutt. But anyway, linear expressions, when you graph them on the coordinate plane, so you can see this no, you can't. So a coordinate plane is, the XY axis, and anytime you graph a linear expression, well, when you set a linear expression equal to y, and you represent it on the coordinate plane, it's going to create a straight line. If that straight line starts at 0 and goes up, that's a proportional linear expression. Now, this is not the only type of linear expression. We can have linear expressions that go downward. We can have linear expressions that don't start at 0. They don't start at the origin. They maybe start up here and they're shallow. We can have really, really steep linear expressions that intersect the y-axis way up high. So linear expressions are called linear because they make a line, linear line. And when I think about lines, I think about one-dimensional objects. So a straight line is a one-dimensional object. The circumference of a circle is one-dimensional, even though it wraps and connects. If we were to peel open a circle, it would make a straight line. So I think of these as linear because all of the variables that are in a linear expression have that power of 1, right? And we don't write it because mathematicians try to omit unnecessary notes. So they have a power of 1, and when things have a power of 1, it's one-dimensional. It makes a straight line, and it doesn't make things that go in different directions, like a quadratic, okay? Quadratics have these like U-shaped graphs, and polynomials that have higher powers, powers greater than 1, greater than 2 even. Quadratics have a power of 2. Polynomials have multiple powers, so this one has a power of 3 because it has 2 humps. It has 1 hump less than its power. This has 1 hump less than its power. And then this is an exponential. Okay, so there's tons of non-examples of linear equations or expressions on a graph. So I know we had a commercial break because the delivery person was here and my dog started barking. I just wanted to check my time. We're at 8 minutes. Okay, so I think this is a decent amount of background. Now some expert tips when you're actually going to operate on linear expressions with addition and subtraction we're going to focus on today. You want simplest form. You want sums, not differences. So I say sums, not differences because remember, terms are separated by addition. And while subtraction is addition, but the opposite, adding the opposite, subtraction can often lead to mistakes because we will be combining like terms and forget that one of the terms is supposed to be actually negative. And I often see mistakes with my students who are learning this skill that they forget to regard the negative sign. So my expert tip is to change all subtraction operations to addition of the opposite. So that subtraction symbol turns into plus a negative versus just subtract. Okay? We want to commute. When we commute terms, once everything's separated by addition, then we can just commute terms around the expression. They can commute back and forth, all around, commute, beep, beep. Think about commuting to work, okay? Commuting means going from here to there. And so when we commute terms in an expression, we can put terms that are next to each other that are alike, like terms. So all the variables, all the terms that have an x variable, and then all the terms that do not, in terms of linear expressions. We only have those two types. We have terms that have a variable to the first power and terms that do not. So that's all we need to work there. Combine like terms, simplify it, and then you want to test to make sure you did your work right. You always want to trust but verify yourself, and then check that they have equivalent values, the expression you started with versus the expression you ended with. So in modeling real life and big ideas math, they're talking about this situation where you buy a product with a coupon and then you want to start selling it to make a profit. So something I actually buy is, let's say, something simple. Let's just think about flour. Okay, so I buy a lot of flour because I've been making a lot of pizza crust lately. And so if I had a coupon that flour was $2 off, okay, per pound. I'm just making that up. I know that Big Ideas Math uses like a skateboard situation. I like to give similar problems for you all so that you can then go back to the examples that are being asked for you to try, and you try yourself without being too influenced by my strategies. That way it empowers you to maybe make your own decisions and use your own strategies. So continue on. So we have a flour $2 off coupon. Okay. And say we also, to a different store, we have a 10% off coupon for a pound of flour. Okay, so in these two situations, what is an expression that we can use to represent how much we're going to pay per pound? So for the brown expression, we have the pound of flour. We'll let F represent the number of pounds of flour bought or used. Okay? So for and we'll use that definition of the variable for both expressions. Now, for the brown coupon situation, we have, for every pound of flour, we get to take off $2. So, actually, the pounds of flour bought or used, can I do this? Can I subtract dollars from pounds? Can you subtract dollars from pounds? No, I can't. This doesn't work. It doesn't work because these are not measuring the same unit of measure. Whenever I'm forming an expression, I need to ask myself, what's the variable and the constant representing, and they need to be representing the same unit of measure. You need to know how much the flour is, so we can use the sub. You need to know how much the flour is. Right, we need to know how much the flour is. Yes, Rebecca, perfect. Okay, so in order to subtract off $2, we need to know how much the flour is. And let's go back to the Big Ideas Math. I know you guys can't see it, but I'm just going to check what their situation is. A skateboard costs $D, and you have a coupon. Let me see if I can just add my window so that you all can see the question. Window, capture. Window capture. I'm going to add the window, and here we go. Okay. There it is. Okay, so a skateboard costs $D for the kit. You have a coupon for $2 off each one you buy. After assembly, you sell each skateboard for $2D minus 4. So the cost is D. So when you sell them, you are selling them for, let me get my face in here for you all, because I know you just want to see my face. I'm just kidding. Okay, so you're going to be selling them for double what you bought minus $4, or double what the original cost of the skateboards were. and then minus $2. And then when you go to resell them, you're taking that original price that you bought, that the skateboards were sold for, doubling it, and then reducing it by $4 for your resale value. Okay, interpret your profit. In our story here, okay, flour is $2 off per pound. So we want F to represent the cost per pound of flour. And Rebecca said that in the comments. This is the first time I've really had comments on the live stream. I really appreciate you guiding my instruction here, Rebecca. Nice. You need to know, yeah. I'm the only one here. That's all right. Hey, then this is a one-on-one learning opportunity for you. You rock. Way to go. Okay. So we are going to remove the window capture. Yes, I want to remove it. And here I am. How can we model real life with linear expressions? Now, Rebecca's here, but another student actually requested this video, Alana, and some other students struggled with this example as well. So I hope that this brings clarity to a bunch of you. Okay, so now we redefined the variable to represent the cost per pound. So now we can use this F minus 2 because F is representing the cost per pound and we're getting $2 off per pound. Okay? If the situation was 10% off per pound, so for the purple situation, it's still going to be cost per pound of flour. But can you think of what this expression might look like? Okay, and actually since we're using the 2, let's change this to 20% off so you all can see the difference of the 2. So the 2s, we can kind of follow the 2. So F is the original price, and we're going to take 20% of the original price and subtract it from the original price. So here's the original price of the flour. Then we take 20% of the flour. Remember, the word of means multiply in mathematics. So 20% of the flour is 0.2 times the flour. 20% is the same as 2/10 as a decimal. 2/10 is the same as 20 hundredths. 20 hundredths is 20%. And then if we remember that we omit crowding notes, this is 1F. 1F minus 0.2F. So if you had $1 and you lost 20 cents, how much would you have? It'd be 80 cents. Okay? And then we can drop that extra 0. It's a placeholder 0, so 8/10 F. Okay, so 20% off turns out to be 8/10 F, where $2 off is F minus 2. All right, so we've set up 2 situations. Now let's think about how much we want to sell a pound of pizzas for, or pizza crusts. Let's just say pizza crust, because then we don't have to consider the cost of the toppings and the cheese and the oils and everything. So if I sold a pound of crusts, let's say I sold them for we're going to resell 1 pound of crusts for twice the original price less $4. And let's see if we make a profit here. Okay? So in which of these cases will we make a better profit? What do you think? What do you guess? So profit, when we think about profit, we're thinking about how much money are we earning? So we want to think about how much we sell the product for and subtract away how much we paid, our cost. Okay, profit is how much we sell minus the cost, and what's left over is what we get to keep in our pockets for our earnings. So profit is sell minus cost. So in this case, okay, we need to figure out how much we're going to sell these for twice the original price less $4. So we want to take, and we're not using D, we're using F, because we're buying flour, not skateboard kits. Okay, so we want to subtract our costs from what we're selling it for. So we have 2F minus 4, and then we need to subtract our cost. This is what we're selling it for. That was our cost for $2 off per pound of flour. Again, here we're going to do 2F minus 4. And we're subtracting how much we paid. So I like doing horizontal setups for adding and subtracting linear expressions because what I can do is line up the like terms. So 2F and F are like terms. They both have an F to the first power. Negative 4 and negative 2. Negative 4 and negative 2, remember we want addition of the opposite. Addition of the opposite. Negative 4 and negative 2 have no variables. They're called constants and they're like terms, so we stack them. Here we don't have a constant. It's kind of like plus 0. We can do that as a placeholder. And then 2F and 8/10 F are like terms. And now negative 4 plus the opposite and 0 are like terms. So now we're actually going to find their differences. So we subtract. So I'm going to start with the constants. Negative 4 minus 2. Negative 4 minus negative 2. Subtracting a negative from a negative. I have negative 4. And I'm taking away negative 2. I'm left with negative 2. Or you can think about the number line. We're at negative 4. We need to subtract negative 2. So we move backwards and we end up here. Okay, I have lots of videos on operations of integers on Muddy Math. Check them out. If I can get to it, I'll link it in the cards here. Okay, so we get negative 4 minus negative 2 is negative 2. And then 2F minus what? How many F's? 1F. We omitted the 1. 2F's minus 1F is 1F. So in this case, we are going to have a profit of F minus 2. So for every pound of flour we sell, positive. What's positive, Rebecca? I don't know what you're talking about. Let me know. Okay, so F minus 2, this is our profit. Okay, so for each pound of flour we sell, we are earning $2 less than the cost of a pound of flour. So as long as the pound of flour originally cost more than $2, we'll be making a profit. If the pound of flour originally cost less than $2, then we're in the negatives. We're not making money. Okay, here, let's try this one. What's negative 4 minus 0? 0 is the additive identity, so it's also the identity in subtraction. Doesn't change. So we have negative 4. And then 2F minus 8/10 F. 2 minus 8/10. 2 minus 8/10 is 1 and 2/10. Think about $2 minus 80 cents. I have $1.20 left. F minus 4. Okay? So in this case, we are earning 120% of the original cost of the flour less $4. So let's say that the original cost of the flour, say that F equals, we're going to pick a value. Say F equals, I don't know, how much does a pound of flour cost? How much does a pound of flour cost? Sorry, the thing is really slow. I was saying that a negative and a negative is positive. So a negative times a negative is positive, Rebecca, but when we're dealing with subtraction, it's not always the case. So like negative 2 minus negative 4 would become positive because you have negative 2 and you're taking away negative 4. You cross over 0 and you end up at positive 2. Negative 4 minus negative 2 stays negative because you're only taking away negative 2 of the negative 4 you have. Negative 4 times negative 2 is positive 8 because you have a negative times a negative. A double opposite becomes positive. So it's really something that the more you practice it, the more second nature it becomes. But until then, it's a little bit like all over the place. So don't worry if you're flip-flopping between the rules. Don't worry about the rules. Just think of the number lines. Think about the concepts. Don't stress about it. So cost of a pound of flour, $4.50. I just looked really quick somewhere. So it's about $4.50. So so we're going to see what our profit would be here. In this case, if we put $4.50 in for F, our profit would be $2.50. And in this case, if we put $4.50 in for F, we would need to multiply 1.2 by $4.50 first, because we multiply in order of operations first, and then subtract away the 4. So it should be about a little bit more than 5. 1.2 times 4.5 is 5.4 minus 4 is 1.4. Okay, so in which case do you make a higher profit? You make a better profit when you're using the $2 off coupon, not the 20% off coupon in this case. Okay, so when I say test with zeros and ones, what I'm saying is, does this expression, f minus 2, is f minus 2 the same as 2f plus negative 4 minus 1f plus negative 2 when we just test it with a 0 or a 1? Okay, we're going to actually find the values of these different expressions and test if they work, and that's always a good habit. So these are written horizontally. I'm going to go ahead and rewrite them vertically, and then we can see what I'm talking about more clearly. Okay, so if I have 2f minus 4 minus f minus 2, is that equal to f minus 2? And then in this case we have 2f minus 4 minus 8/10 f. Is that equal to 1.2 f minus 4? And the best way to check these things is if you just use friendly numbers like 0 and 1. So if I use 0 and 1, try to remove those reflections, for f, okay, if I put in 0 for f here, 0, 0, okay, it's a quick way to check because zeros cancel out and it's the additive identity. So 2 times 0 is 0, minus 4, minus 0 minus 2 is negative 2, okay, equals 0 minus 2 is negative 2. So then I simplify in the parentheses, I get negative 4 minus negative 2, and I'm asking myself, is that equal to negative 2? Negative 4 minus negative 2 is the same as negative 4 plus 2, which is equal to negative 2. So that one works. Very good. Let's try with ones down here. I plugged in a 1 for all the f's. Would the two expressions on either side of the equal sign, do they work out? Are they equal? And if they are, that means I did subtract or add the expressions correctly. Okay, so I have 2 minus 4 in these parentheses minus 8/10 times 1 is 8/10 equals 1.2 times 1 is 1.2 minus 4. 2 minus 4 is negative 2 minus 8/10. So here, Rebecca, I have negative 2. So if you think about the number line, negative 2 minus 8/10. So I'm getting more negative. I'm subtracting a positive value. So if I'm on the number line, here's 0, negative 1, negative 2, and I subtract 8/10. I'm getting further from 0. I'm going downward. I'm subtracting a positive, so I move forward. So I end up at negative 2.8. Is that equal to 1.2 minus 4? 1.2 minus 4, on the other hand, is up here. Here's 1. Here's 1.2. I need to subtract 4. So I'm going 1, 2, 3, 4. Okay? Yes, and it does land at negative 2.8. Here's 3. Okay? That's negative 2.8. That's 3. So my number lines aren't perfect. It's just a quick visual, conceptual thing. So I'm starting at positive 1.2, and I'm going subtracting a positive, so I'm going downward and moving forward. So 1, 2, 3, 4, I end at negative 2.8. So yes, both of my subtracting of linear expressions worked. No idea how long this took. I hope this helps. Thank you for tuning in, Rebecca, and keeping me focused on questions and being interactive. You're amazing. I hope this helps. Alana and all the other students that requested videos. I think Kylie requested this video as well. And maybe, I don't really remember. But have a great Friday. Cheers to you all. Be well. I'll see you soon.